this video, I want to revisit our discussion of kinetic energy and how it applies to rigid bodies undergoing motion. So recall again that we have this equation T1 plus U1 to 2 equals T2, where we have kinetic energy terms, 1 and 2 on either end, and work being added to or subtracted from the system in the middle with U1 to 2. So if we think about specifically the kinetic energy terms, we can think about the different forms of motion that are possible for our rigid body. So for translation, we might say that, okay, we have a rigid body and it's undergoing some sort of motion such that it has a velocity v, which is the velocity of that center of gravity. And for this rigid body undergoing or moving with some velocity, we can calculate its kinetic energy as a result as 1/2 mv squared. We can look at the same sort of thing for rotation or fixed axis rotation. If we have a rigid body, center of gravity, undergoing a rotation, angular velocity with an angular velocity, then we can express this rotation and the energy of it in terms of its moment of inertia about the center of gravity times its angular velocity squared. The limiting condition, though, of this expression is that we are looking at rotation specifically about the center of gravity. So what if instead we have a rigid body with a center of gravity here, but a rotation center I'm calling point A down here. So we have this point A about which we have some angular velocity, omega. And if this is the case, then the center of gravity itself is moving with some velocity, which I'm going to call v sub g. Now, under this condition, if we want to calculate the kinetic energy of the situation, we have, generally speaking, a rotation component about with the moment of inertia about the center of gravity, but then we also have to take into account the fact that the center of gravity is itself moving. So we have a 1/2 mv squared term in there. Now we can make some adjustments or simplifications to this. Suppose we recall that we can relate the velocity, the linear velocity of g, to omega by the distance between them, which is v equals r omega then. So if we take that and plug it into this equation, we get t equals 1/2 times ig plus, oops, forgot the g there, plus mr squared omega squared. So substituting in that vg term into the second expression, and I get something that looks like this. Now this middle term here looks like the parallel axis theorem. So if I take that into account, that this middle term is parallel axis theorem, then, so therefore, I can rewrite my kinetic energy equation as 1/2 IA omega squared. So the key difference here being that I'm taking the moment of inertia about point A, which is my rotation center, and usually to get my moment of inertia about point A, I'm going to take the moment of inertia about point G, which I possibly know from any common geometries, and I'm going to apply or add on to it that term that goes along with the parallel axis theorem. So as a result, I get the same equation as long as I take into account that parallel axis theorem term. So ultimately, our goal would be to put these two things together, the energy of fixed axis rotation and the energy of translation, such that we can account for any general planar motion. And we'll see that in the next video. Thanks.